In the context of a portable generator lacking a direct bond between its windings and the frame or grounding lugs, a ground fault current, in the traditional sense, cannot readily return to its source, even with a ground rod installed and connected to the generator's frame. This is because a complete circuit for the fault current to flow back is absent. However, the absence of a direct ground connection does not eliminate the risk of ground faults. A ground fault arises when electrical current deviates from its intended path and flows through an unintended path, such as a person touching faulty equipment. This situation poses significant hazards, potentially leading to severe injury or even fatality due to electric shock. Ground fault circuit interrupter, or GFCI, receptacles play a crucial role in mitigating these risks. These devices are engineered to safeguard individuals from ground faults by continuously monitoring the current balance between the hot and neutral conductors within a circuit. If a discrepancy in current flow is detected, signifying a ground fault, the GFCI receptacle swiftly interrupts the power supply, effectively preventing electric shock. Here is a deeper dive into the functionality of a GFCI receptacle. It incorporates a compact transformer featuring two windings, namely a primary winding and a secondary winding. The primary winding is electrically connected to the hot and neutral wires within the circuit. Simultaneously, the secondary winding is linked to a sensing coil. The sensing coil is meticulously designed to identify any disparity in current flow between the hot and neutral wires. The presence of such a difference suggests a ground fault condition. Upon the sensing coil detecting a ground fault, it triggers a switch mechanism that promptly opens the circuit. This action cuts off the power supply to the circuit, thereby impeding the flow of ground fault current and minimizing the risk of electric shock. GFCI receptacles stand as indispensable safety apparatuses, offering vital protection against ground faults. Their integration with portable generators is paramount, irrespective of whether the generator is grounded or not, to ensure the safety of individuals operating the equipment. It is important to remember that while a portable generator not bonded to ground cannot have a return ground fault path, a GFCI will still protect you in the event of a ground fault. First, GFCI receptacles offer a crucial layer of protection against electrical shock by quickly de-energizing a circuit when a ground fault is detected. Second, the GFCI receptacle contains a differential transformer that monitors the current flow in the hot and neutral wires. Third, when a ground fault occurs, the current flow in the hot and neutral wires becomes unbalanced. Fourth, the differential transformer detects this imbalance and trips a relay, which opens the circuit. Fifth, this interruption of the circuit occurs very quickly, typically in a fraction of a second, minimizing the duration of the electrical shock. Sixth, even without a direct ground connection from the generator to earth, the GFCI can still function effectively because it is monitoring the current balance within the circuit itself. Seventh, the absence of a ground connection does not negate the risk of a ground fault occurring. Eighth, if someone comes into contact with a live part of an ungrounded generator and also provides a path to ground, such as by touching a grounded object, a ground fault can occur. Ninth, in such a scenario, the GFCI will still detect the imbalance and trip the circuit, providing protection against electrical shock. 10th, it is advisable to always use GFCI protected receptacles with portable generators, regardless of whether the generator is grounded. 11th, this practice ensures an added layer of safety for both the user and those nearby. It is also important to note that even though a generator may not have a direct bond to ground, proper grounding practices should still be followed whenever possible. This may involve driving a ground rod and connecting it to the generator frame, as this can help to reduce the risk of electrical shock and improve the overall safety of the electrical system. If the generator is used to power equipment that requires a ground connection, it is important to ensure that the equipment is properly grounded. This can be done by connecting the equipment's ground wire to a suitable grounding point, such as a ground rod or a grounded metal enclosure. The function of a ground fault circuit interrupter, or GFCI, is rooted in the principle of monitoring the current balance between the supply conductor, often the hot wire, and the return conductor, often the neutral wire. In a properly functioning electrical circuit, the current flowing through the supply conductor should be equal to the current returning through the return conductor. The GFCI device is equipped with a differential transformer, which is specifically designed to detect any imbalance between these two currents. When a ground fault occurs, a portion of the current deviates from its intended path and flows through an unintended path, such as a person's body, to ground. This diversion of current creates an imbalance between the supply and return conductors. The differential transformer within the GFCI is highly sensitive to this imbalance and is calibrated to detect even minute differences in current, typically in the range of 5 mA. Upon detecting an imbalance exceeding the threshold, the GFCI device swiftly activates a tripping mechanism which interrupts the flow of electricity to the circuit. This interruption occurs within a fraction of a second, typically within 20 to 30 milliseconds, effectively minimizing the duration of the electric shock and reducing the risk of serious injury or death. The swift response time of the GFCI is crucial in preventing severe electrical accidents. The GFCI device is engineered to protect individuals from the hazards of ground faults by promptly de-energizing the circuit when a fault is detected, thereby mitigating the risk of electric shock. It is important to understand that a GFCI does not protect against overloads or short circuits. Overloads occur when the current flowing through a circuit exceeds the rated capacity of the wiring or circuit breaker. Short circuits occur when there is a direct connection between two conductors, such as the hot and neutral wires. Overloads and short circuits can cause the wiring to overheat and potentially start a fire. Circuit breakers and fuses are designed to protect against overloads and short circuits by interrupting the flow of electricity when these conditions occur. While GFCIs do not protect against overloads or short circuits, they do provide an additional layer of safety by protecting against ground faults. Ground faults can occur when there is a break in the insulation of a wire, allowing current to flow to ground. This can happen if a wire is damaged, or if it comes into contact with a metal object. Ground faults can be particularly dangerous because they can cause electric shock. GFCI receptacles are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of exposure to water. It is important to test GFCI receptacles regularly to ensure that they are working properly. This can be done by pressing the test button on the receptacle. If the receptacle trips, it is working properly. If the receptacle does not trip, it may need to be replaced.